Up to this point, we've dealt with explicit formulas for sequences. The general term of a sequence formula defines the relationship between the term number and the term itself. So meaning in this example, Tn equals 2n minus 1. The independent variable is n, and the dependent variable is Tn, and they're related. Okay, so if you want to know the 10th term, all you need to plug in into the equation is plug in n equals 10, and you would get the 10th term as 19. All right. A sequence can be defined recursively. This is new for this lesson. If each term can be calculated from the previous term or terms. A recursion formula shows the relationship between the terms of the sequence. So in this example, 1, 3, 5, 7, we've covered this before. The explicit formula is 2n minus 1, or if you want to use function notation, f of n equals 2n minus 1. And we get that by using the general form or general term of an arithmetic sequence. Plug in 1 for A, plug in 2 for D, simplify, and that's how we get 2n minus 1. This means that the term depends on the term number, so the term Tn depends on n. The recursion formula for this exact same sequence would be T1 equals 1, so I'm telling you the first term, and Tn equals Tn minus 1 plus 2, n is greater than 1. Tn is the next term. Tn minus 1 would be the previous term. If we were to write this out in words, we would say that the next term is equal to the previous term plus 2, 2 being the common difference. And we have this restriction that n has to be greater than 1 so that our term numbers are always whole numbers. So up to now, the general term that we've discussed, that is the explicit formula. Okay, now we're learning about recursion formulas. So let's go over a couple more examples. All right, in this example, T1 equals 1 means the first term is 1. Tn equals Tn minus 1 plus 1. This means the previous term plus 1 is equal to the next term. So if we write out the terms, the first term would be 1. The next term we would have to add 1, so 2. The next term again add 1, so 3. The next term add 1, 4. Try the next example on your own. Pause here. For example B, the first term is 2, and 3 times the previous term plus 5 gives us the next term. So use that formula to figure out the first 4 terms in the sequence. 2. The next number is going to be 2 times 3 plus 5, so 11. The next number is going to be 3 times 11 plus 5, so 33, 38. And then the next number is going to be, running out of room, 3 times 38 plus 5, I believe is 119. Okay, move on to the next video. All right, we're finishing up page 1 of lesson 7.4. So since we know how to get the explicit formula for an arithmetic or a geometric sequence, we're now going to learn about how to change them to their recursion formulas and vice versa. So given an arithmetic sequence, you already know this from lesson 7.1. the general term of the arithmetic sequence is Tn equals a plus n minus 1 d. But the way that we get this explicit formula was because we could just keep adding d to get to the next term. So the third term would be a plus 2d, the fourth term would be a plus 3d. So as the recursive formula, we would just need to write down that the first term is equal to a, and every subsequent term is going to equal the previous term plus the common difference d. And don't forget the restriction on n. It has to be greater than 1, just to make sure that the term numbers are whole numbers. Okay, positive greater than 0. All right, one more time, just to make sure. Here, the general term of the arithmetic sequence is given as an explicit formula. This is the recursive formula for the arithmetic sequence. All right, let's move on to the next page for geometric sequences. Same deal with geometric sequences. We can express them using an explicit formula as well as a recursive formula. Again, recall from all the way back, lesson 7.1, the general term of a geometric sequence was a r to the exponent n minus 1. That's the explicit formula. And now the recursive formula, remember, we just need to multiply the previous term by r, and that's how we get the next term in the geometric sequence. So let's write that out. The first term is going to be a, and the next term is going to be the previous term times r. And n has to be greater than 1. Again, make sure our term numbers are whole numbers. Once more, the recursive formula, T1 equals a, the first term. The next term is equal to the previous term times the common ratio r, and n has to be greater than 1. So let's go over some examples. Looking at example A, I can see that I have to add 3 to get to my next term. So this is an arithmetic sequence. The explicit formula for an arithmetic sequence, Tn equals a plus n minus 1 d. Plug in everything you know, negative 10 plus n minus 1 times 3. And when you simplify, you should get 3n minus 13. And that would be your explicit formula. Refer back to the bottom of page 1 if you need to. The recursive formula for an arithmetic sequence is T1 equals a, and Tn is equal to Tn minus 1 plus d. So the next term is equal to the previous term plus the common difference. N is greater than 1. So just plug in everything, and you're done. So T1 equals negative 10. Tn is equal to Tn minus 1 plus the common difference 3. N is greater than 1. And that gives us our recursive formula. All right, feeling good? Let's try the next example. It's a geometric sequence this time because we need to just multiply by negative 3 every time. So that's how we know we have a geometric sequence. So Tn equals a r to the power of n minus 1. So 2 times negative 3 to the power of n minus 1. That's our explicit formula. For the recursive formula, I know it's T1 equals a, Tn equals r times Tn minus 1, n is greater than 1. So T1 equals 2. The next term is equal to negative 3 times the previous term, n greater than 1. And that's the recursive formula. We'll go over some more examples in the next video. All right, we're at the bottom of page 2 of lesson 7.4. So some sequences, they may be a bit more challenging to determine their recursion formula. The best advice that I can give you is try to determine the pattern that's going to get you from term 2 to term 3 and then from term 3 to term 4, and then term 4 to term 5, so on and so forth. So in this example, determine the recursive formula for the sequence 1, 3, 6, 10, 15, 21, etc. What I'd like to do is write out the terms like so. So T1 is equal to 3. Nope, sorry, T1 is equal to 1. Hold on. Thank goodness for whiteout. All right, and now the second term is equal to 1 plus 2, meaning the first term plus 2. You can see that right there, plus 2. All right, I'm going to try this again. T3, the third term, is going to be 3 plus 3. So the second term plus 3. And keep this going. The fourth term is equal to 6 plus 4. So the third term plus 4, so on and so forth. Right? If you notice, the numbers that you're adding on each time, they increase by 1. And they are the same as the term number n. Alright, so now that I've detected this pattern, what I can do is I can say T1 is equal to 1, and then the next term is equal to the previous term plus n. And n has to be greater than 1, as usual. And I've written out the verbal description for you here. Alright, last example, so turn to page 3. This is a word problem. So I want you to read the question, the example, and highlight some of the key points, and then write down what happens to the medicine in the runner's body over time. So answer A. Pause the video and do that now, please. Alright, so you can see I highlighted a couple of key points. Every 4 hours for 3 days, this runner is going to be taking an anti-inflammatory medicine. And the half-life of the medicine is also 4 hours, meaning that after 4 hours, approximately half of the medicine is still in the body. So half of it has decayed, gone away. So describe what happens to the medicine in the runner's body over time. Well, after one dose, the amount of medicine in her body would decay or decrease to half its original amount. So I'm going to write that down right now. So I've written that first part down, but you also need to remember that she is still taking an additional dose every 4 hours. I'm going to write that down as well. So I've color coded, highlighted the information, adding a new dose of 500 milligrams, that's every 4 hours. Okay, amount of medicine decreases to half, that's the half-life. So for part B, write the amount of medicine remaining after each 4-hour period as a sequence. I'm going to create a table. So I've made this little table with the dose number up at the top going across. This is the number of hours that have passed, and this is the amount of medicine in her body. So with the initial dose, she has 500 milligrams of the medicine in her body. Now, the second dose of medicine, so this is now 4 hours after the first dose, this 500 milligrams has decayed to half. So there's 250 milligrams remaining. But she also adds in a new 500 milligram dose. So that means her total is going to be 250 plus 500, 750 milligrams of medicine in her body after 4 hours. Repeat this pattern for the third dose. So 8 hours have passed. So this 750 gets multiplied by half, and then we have to add the 500 afterwards. Pause right now, fill in the rest of the table for 3 and 4. Alright, so if we were to describe what's happening in her body, we would always take the previous dose, multiply that by half, and then add a new 500 milligrams. So pause and write the recursion formula. And there we have it. The first dose is 500 milligrams, and the second dose is that times half plus 500. Sorry, I just wanted to make one little correction. My apologies, I ran out of time in the last video. Sigh. Alright, so originally I'd written down that n has to be greater than 1, but there is still one more restriction. So n has to be greater than 1, and it has to be smaller than or equal to 18. Okay. And the reason for the 18 is because of this at the top, the runner was prescribed the medicine every 4 hours for 3 days only. So this is going to be 6 times a day, so which is every 4 hours, right? Multiplied by 3 days equals 18 doses maximum. All right, so that's just the upper limit. So that's it for recursive sequences. Thanks.